Right. So for the last couple of weeks, we have uh, done basically calculus of two variables. The calculus, we say that is limit. This is last chapter. And differentiations. So this chapter 12. And now we have the integrals. Chapter 13. Okay, so we'll cover this one. Okay. So let me remind you the idea of the integral. Okay, so the basic thing is uh, suppose you have just one variable, just the main idea. You have f functions. On a closed interval AB. Okay. First, you want to find do some partitions. Partitions the interval. So this is what you do. Okay. And then take a sample. Say this one. Okay. So this is the sample. So aj minus 1 to xj. And with the height is determined by the height of some representative of this subinterval. Okay. Take a sample and then you compute the area of this rectangle. Rectangle is f of xj star times this one, xj minus xj minus 1. This is what we call the delta jx. Okay. And then the third is the makes the partition finer. Oh, sorry, sum them up. You sum all these rectangles, so you get this one. So you sum them up over partitions P. Okay. Partition P. Okay. So this gives you f of xj star delta jx. Okay. And the fourth, take limit. As the partition gets finer, or we say that the norm of partitions goes to 0. We call this is the maximum of xj minus xj minus 1. So 1, 2, say n. Okay, so the largest one. Okay, take limit. If limit exists, then this is called the integral. Limit of this Riemann sum. Okay, this is from Riemann Sum. Okay, so this is the process basically. Partition, take sample, sum them up, take limit. All right, so we would like to do this over for two variables now. So this is the idea. So now we have that z equals f of x of y. So function of two variables now. Over the rectangle R, AB cross CD. What does tell you? Oh, this is the range of x, this is the range of y. Okay. Let us assume first that the f continuous. Let's see. Got. So as we have a rectangle, so this is and then what we have is this. So between A and B and C and D, X, Y. Okay. So what we do here is do some partition here. Okay. So the process is the same. So we copy the process as what we have in so let's say copy the process of integral of one variable. Okay. So here we first copy, we do some partitions. So, but our partition now is partitions now into small rectangles. So a bunch of small rectangles. So what we have, so okay. So for example, this is our sample. Sample rectangle there. So here we have xj minus 1 xj. This is what we have yk minus 1 yk. Okay, so small rectangles. So this rectangle here is this is delta jx. This is delta ky. Okay, so that's one. Okay, so this is the partitions. So for x, and the 1y, 2y, say ym is d, this is d. So this is the partitions, okay? And then second is take sample, okay? So this is our sample. Of length delta j x delta k y, okay? And take a representative. Okay, that representative is, say this is x j k star. Okay, so our sample is now a uh, let's see, is now a what do you call, not really a cube. There. Okay. X, Y. So the height is determined uh, the what do you call, the area of the base area is what we call delta ija. Okay, and the height is f of k. Okay, so when we the product uh, sorry, I should say xj yk. Okay, uh, xj yk. So okay, so when we form this delta jk, yeah, that is the volume of this uh, how you call this stuff, a box. Okay, all right, and the third you sum over these partitions f star, and as take limit as the partition gets finer and finer. Okay, and if limit exists, then this is what we call the double integral of f with variable fy a over rectangle R. Okay, so this limit, same thing. So this is what we call double integral uh, of f over the rectangle R. Okay, and from the constructions, we know the meaning of this. Uh, of the integral, double integral, say, I should say. Volume. Okay. So the volume of a solid uh, under the surface would be equal f of x over the rectangle. Um, okay, that's what it means to be the double integral. So this the notion of a what we call a double integral. So for example, one, say if we, this is assuming f is non-negative. Okay, so assume first f is defined on this rectangle. Plus 0, 4, for example. Okay, such that f(x) of y, the value is say 1 if x between 0 and 1, and y is the whole thing. 2 if x between 1 and 2, y can be anything in between. So this is how we define the function. Okay, so it looks like this one here. Okay, so this is I should say the other way around. Okay, so 3, 2, 1. Okay, so let's see, 1, 2, 3, 1, 2, 3, 4. So the picture looks like this one here. So height 1 here. Okay, so here you have height 1. Okay, and then you have height 2. And last you have height 3. Okay, so in this case, this integral is our R. It's the volume of this, say, 3 boxes here. Okay, so the first one is the first one here. Let me put the number. Okay, so 1 plus 2 plus 3. Okay. So 1 has a volume of, let's see, this is just length 1 with 4, height 3. Okay, and 2 is height, length, say width 1, length 4, height 2, and the 3 is length 1, width 4, height 1. Okay, so basically just 12, 8, and 4 times. Okay, so 24. So that's the idea of the double integral. Okay, questions? Questions so far? Okay, let's go to the textbook. See some more example. All right, first about existence. What kind of functions can we compute here? So this tells the integrability theorem tells you that requirement. Okay, I suppose f is bounded on a closed rectangle R, and it is continuous except on a finite number of smooth curves. Then f is integrable over R. In particular, if f is continuous, then it is integrable. Okay, so let's copy this one. Where is the capture? This is basically the idea if what kind of function can we compute the integral? Okay, so continuous functions, or more generally, continuous except on some finite number of curves. Okay, then it is integrable. Okay, so we can compute with this. The key question, next key question is how do we compute it? All right, so let's go to the, okay. For example, this is a continuous functions. So we should be able to compute this one. For example, this is continuous. Sine trig function is continuous. So exponent of the sine is a continuous. Y cube is polynomial, continuous. Cosine of the polynomial is continuous. Okay, so this is continuous. So it ought to be integrable, okay, on every rectangle. On the other hand, this g here is a bit problem here because this is not defined at a y equals x squared. Okay, so in the parabola. Okay, and this won't be bounded on this on uh, on rectangle containing the parabola, part of the parabola. Okay, so example, let me just again. Okay, so this one. Continuous. On any rectangle. Therefore continuous. Therefore integrable. On the other hand, here it's not defined on the parabola square. Okay. So in fact, this is xy. Here we have. Okay. In fact, this is unbounded. On any rectangle. Sorry, you should have this one. Containing any part of the parabola. Okay. So this is not integrable, for example, here. Okay. But if you take the square here, not the square, but rectangle here, this square avoids, therefore key is continuous and bounded on this R, say R star. Therefore integrable on R star. Okay. So as long as we avoid the bad things. Okay, so that's what we mean by integrability. Okay, questions? All right, if not, then we come to this property, we just use them. Okay, suppose we have a integrable function, then a multiple of that integrable functions, kf. You can take that k out, factors k out. Okay, so you get this one, as usual. You have a sum of integrable functions is also integrable, with the integral is the sum of the integral. Okay, so here you see the left-hand side, you integrate sum of function. Okay, and then on the right-hand side, you see the sum of integral, sum of double integral. Okay, so apparently these two operations, double integral and addition of functions, commutes. You can here on the left-hand side, you can add first, do addition first, and then integrate. Here on the left, right hand side, you integrate each one first, and then sum the second. Okay. So this operation, these two operations, double integral and addition, is switchable. You can switch the order. Same thing if you have negative, then you can subtract also. Okay. So if you have this is additive means you have rectangle R consists of two smaller rectangles, say R1 and R2. Okay, if you integrate over the bigger rectangle R, that's the sum of the double integral over the two small rectangles over R1 over R2. So that means what we call there's the additive. Okay, and we have also comparison property that if F is below G on that rectangle R, then the double integral also uh, that order also applies for the double integral. If F is less than G, then the double integral of F is less than double integral of G. Okay. All right. So we see this one here. If in particular, if F is 1, right? So for example, you integrate K over dA, K with dA. You can take the dA out, and this integral here is just area. Okay. So here. This is just example that we one that we did earlier. Okay, so this is just a. All right, so let's uh, we'll start with the next section. Just the idea. So the question is, how do you compute the integral? Double integrals. Okay. So this is the method of the technique. So this is the concept of the double integral, and how we see this one. All right. Um, so let's see here. And right, this is A and B, C and D. Okay. And all right. The thing here is that how do this double integral is over this is R A B plus C W the graph. All right, so let's see this one, or X Y A D A. Okay, let's see how do we compute this one. All right, so let's proceed. Uh, this is just one method to compute the sum. Uh, let's proceed by row or uh, by a column here. Okay, so first let's proceed by row. Row meaning, all right, so let's see. Okay, so then we have this one. So this is X1, X1, X2. So proceed by row. If we proceed by row, let's see. So here proceed by row. So we have this one. Okay. Okay. So in this case, we fix the k. So this is y k minus 1 y k. Fix k. So in this case, we fix the y variable. Okay. So what we sum is this one here. So first we compute this one. Is first by row, rowing, so it's called, sorry. So the x move, okay. Right. Okay. So by row, yeah. So this is what we have. F of x k y, sorry, this is j y k. Okay. So this delta j x. Okay. This is j. This is going by row. So this column 1, column 2, column 3, and so forth. So from j equals 1 till say m. Okay. And then you sum the column. Okay. So this is how we proceed by row. And if you recall this part here, well, this one is fixed. So if we delta j goes to 0, uh, say partitions go to 0, I just say this. This goes to, this is the Riemann sum. If you take the limit of the partition goes to 0, you get this integral. Okay, so integral of x respect to x, and the y is fixed. Dx. So from x equals a, from to x equals b. Okay. So when you sum this up, now the whole thing, again, this is like an integral. So what's inside is this integral. Okay, so this is what you have is sigma of k from 1 to n. Like this. So say this is a f of y, yk. So in fact, this is a Riemann sum. Okay, so the whole thing is Riemann sum that goes to integral of this thing. So what is this? Well, that's nothing but y c equals c. Now for the capital F. Okay, so that means this is what we call the iterated integral. Iterated meaning that it's something that you apply over and over, repeated integral. Okay, because you do integral with one variable first, and then to the second variable. Okay, so similarly, R is R. Okay. So this is the iterated integral. You can write as this one, or you can also write as This is the CT. This is A and B. Y. Okay, notice this the order of this. Okay, so this is X. This is Y. So this is bound of Y. This is bound of X. Similar thing here. So this is bound of Y. This is bound for X. So the conclusion is that iterated integral is the way to compute the double integral. Okay, so you see you can do both ways. You can do X first, integrate X first, or integrate Y first. Doesn't matter. Okay, any questions? All right, oh, forget. So the question is, what is dA actually? This is our dA. So in this case, dA actually dx over dy, or y for dx. Okay. Show you a couple example. Let's take an example here. Okay, so suppose we have a function, a surface like this. Okay, so if you proceed, you make a slice, okay, with y constant, so constant. So x varies, y constant. So you like make a slice like this. Okay? So you compute the volume of this slice. Okay, so volume of this slice is the area. Slice. Okay, and then you compute again the whole thing, integrate. So this is iterated. Okay, so this is what we have. Okay, so this is a example. Simple example. I won't write it. Rewrite this. Just read it. So integrate 2x plus 3y, dx dy. So this is the x. This is y. Okay. So if you do the integral with respect to x first, okay. So compute this one, this x. Oh, like this, just like x squared. This is, well, when you integrate with respect to x, everything containing y, you think that's as a constant. Okay, so this is what we have. So this is the reverse of a partial derivative. Okay. All right, so if we compute this, you get 3 plus 3y. Okay, so the x will vanish. Everything with the x will vanish because you substitute this 1 and 2 for x. Okay, so what's remained is y. Then you put this 3 plus 3y into this integration, the outside integrals. So from 0 to 3. Okay. And you get this number. or this example here. The other way around. So you switch the order. Okay, it's the same function, but switching the order. So here you have dx dy. Here we compute dy dx. So if you compute respect to y first, 2x with respect to y is constant. We just get 2xy. Here we have y squared. Plug in the numbers, plug in the bounds. You have this. Put into the second integral, you get the same thing. Okay. All right. I think we'll stop here, take a break, and we'll continue in 5 minutes. All right. So let's